Imagine holding the entire history of everything you have ever loved in the palm of your hand. Every sunrise you have ever watched, every warm afternoon, every shadow a tree ever cast across summer grass. All of it, every single moment of life on this planet, powered by one ancient extraordinary star that has been burning faithfully in the darkness for 4.5 billion years. The sun is not just a light in the sky, it is the author of life itself. And its story, where it came from, what it is, and where it is going, will change the way you see everything. Right now, at this very moment, you are being kept alive by a star, not metaphorically, not poetically, literally. Every breath you take, every heartbeat, every thought forming behind your eyes, all of it is powered, directly or indirectly, by a colossal ball of plasma burning 93 million miles away. We call it the sun, and most of us take it entirely for granted. We see it rise, we see it set, and we carry on with our lives without ever stopping to ask the most astonishing question of all. Where did it come from? What exactly is it doing right now? And what will happen when it finally dies? Because it will die. Everything does. And the story of how the sun was born, how it lives and how it will end, is one of the most breathtaking stories that science has ever uncovered. To understand the sun, you have to go back, not years, not centuries, but billions of years, to a time before the sun existed at all. About 4.6 billion years ago, the region of space where our solar system now sits was cold, dark and empty-looking. But it wasn't truly empty. Drifting through that darkness was an enormous cloud of gas and dust, mostly hydrogen and helium, with tiny traces of heavier elements mixed in. A cloud so vast it stretched across dozens of light years. Astronomers call this a solar nebula. For an immense stretch of time, this cloud simply floated, cold and inert, doing almost nothing. Then something disturbed it. The leading theory is that a nearby star died violently, a supernova explosion that sent a shockwave rippling outward through space. When that wave hit the nebula, it compressed regions of the cloud, making parts of it denser than others. And the moment density increases, gravity takes over. Gravity is not dramatic, it is not loud, but it is absolutely relentless. The denser regions of the cloud began pulling material inward, collapsing slowly under their own weight. As the cloud contracted, it began to spin. A natural consequence of physics, the same reason a figure skater speeds up when pulling their arms close to their body. The rotation flattened the collapsing cloud into a disk, and at the center of that disk, material was piling up rapidly, compressing under enormous gravitational force. As this central mass compressed, it heated. The gravitational energy of all that infalling material converted into heat, and the temperature at the center climbed steadily. From the near absolute zero of open space, through thousands of degrees, then hundreds of thousands, then into the millions. A glowing, furiously hot ball of gas was forming at the heart of the disk. This object, not yet a true star, not yet capable of nuclear fusion, is what astronomers call a protostar. It shone not from nuclear reactions, but purely from the energy of its own gravitational collapse, a process called Kelvin-Helmholtz contraction. For roughly 100,000 years, the young sun existed in this protostar phase, glowing brilliantly while continuing to compress. Then, at a core temperature of approximately 15 million degrees Celsius, the threshold was crossed. Hydrogen nuclei, single protons, were moving fast enough, were packed tightly enough that they began to collide and fuse together. Hydrogen became helium, and in the process, a tiny fraction of mass was converted directly into energy, exactly as Einstein's equation predicts. The first nuclear fusion reactions in the sun's core ignited, and in that moment, a star was born. The ignition of fusion did something profound. It didn't just produce energy, it produced a force pushing outward, counteracting the inward pull of gravity. These two forces reached a balance. gravity ceaselessly trying to crush the star inward, and the pressure of fusion-generated radiation pushing back against it. This equilibrium is so precise, so finely tuned, that it has held without breaking for 4.6 billion years. Astronomers call it hydrostatic equilibrium, and it is the defining condition of a stable, healthy star in the prime of its life. In the Sun's core right now, about 620 million metric tons of hydrogen are being fused into helium every single second. That figure is difficult to truly absorb. And yet the Sun contains so much hydrogen that it can sustain this rate of burning for roughly 10 billion years in total. Since the Sun is currently about 4.6 billion years old, we are sitting almost exactly at the halfway point of its stable life. The Sun is, in cosmic terms, a middle-aged star. The energy produced in the core embarks on one of the strangest journeys in all of physics before it ever reaches your skin. A photon of light generated deep inside the Sun does not shoot straight outward. Instead, it is immediately absorbed by surrounding plasma and re-emitted in a random direction. Then absorbed again, re-emitted again in another random direction. This process repeats millions upon millions of times. The photon is essentially trapped in a random walk through the densely packed interior of the Sun. The result is staggering. It takes a photon of light somewhere between 100,000 and 1 million years to travel from the Sun's core to its surface, a journey of only 430,000 miles. Once it finally escapes from the surface, it crosses the 93 million miles of empty space between the Sun and Earth in just 8 minutes and 20 seconds. The sunlight warming your face right now was generated inside the Sun more than 100,000 years ago. You are bathing in ancient energy. The surface of the Sun, called the photosphere, glows at around 5,500 degrees Celsius, but above it sits a thin, reddish layer called the chromosphere, and above that is the corona, a ghostly halo of superheated plasma extending millions of miles into space, with temperatures exceeding 1 to 3 million degrees Celsius. Here is one of the great unsolved mysteries of solar physics. The corona is far hotter than the surface below it. That's like standing next to a fire and feeling it get warmer the farther you walk away. It defies intuition. Scientists believe the answer involves magnetic energy being released through processes like magnetic reconnection and plasma waves, but a complete explanation still eludes us. The Sun's magnetic field is generated by the churning, swirling motion of its electrically charged plasma interior, a self-sustaining process called the solar dynamo. This magnetic activity creates sunspots, which are darker, cooler regions where intense magnetic fields suppress the normal flow of heat to the surface. It creates solar flares, sudden violent bursts of radiation that can disrupt satellites and communications on Earth. And it creates coronal mass ejections, enormous clouds of magnetized plasma hurled outward into space at millions of miles per hour. These eruptions interact with Earth's own magnetic field, sometimes causing spectacular auroras near the poles, and in extreme cases, threatening power infrastructure on the ground. The largest recorded solar storm, the Carrington event of 1859, was powerful enough to set telegraph equipment on fire. A similar event today would be catastrophic for modern civilization. The Sun also streams a constant flow of charged particles outward in all directions. This is the solar wind, and it permeates the entire solar system. It sculpts the tails of comets, always pushing them away from the Sun, regardless of which direction the comet is traveling. It carves out the heliosphere, the vast bubble of space influenced by the Sun, which extends far beyond the orbit of Pluto and represents the true edge of our solar system's reach. The Sun is not static. Even during its stable main sequence life, it is slowly, imperceptibly changing. When it first ignited 4.6 billion years ago, it was about 30% less luminous than it is today. As the core gradually fills with helium ash, the byproduct of hydrogen fusion, the hydrogen-burning region contracts and heats up slightly, producing more energy. The sun grows slowly, steadily brighter and larger over billions of years. This has a disturbing implication for Earth. In roughly 1 billion years, the sun will be bright enough to trigger a runaway greenhouse effect, boiling away Earth's oceans. Life on the surface will become impossible long before the sun undergoes its dramatic final transformations. The planet we call home has a biological expiration date, and it is measured in hundreds of millions, not billions, of remaining years. In about 5 billion years, the hydrogen in the sun's core will finally be exhausted. Fusion in the core will stop. Gravity, no longer opposed, will begin to win. The core will start to collapse under its own weight, heating up rapidly as it does so. This heat will ignite a shell of hydrogen surrounding the dead helium core, and in a seemingly paradoxical response to a core that is shrinking, the sun's outer layers will begin to expand enormously, dramatically, and relentlessly. The sun will swell into a red giant, growing to perhaps 100 to 200 times its current size, its surface cooling to a dull, reddish glow, while its total brightness climbs to perhaps 1,000 times what it is today. Mercury and Venus will be engulfed and vaporized. Earth may survive the expansion itself, as the sun loses mass during this process, causing Earth's orbit to drift outward. But it will be a scorched, airless, completely lifeless rock either way. As the core continues to compress, temperatures will eventually reach approximately 100 million degrees Celsius. At that threshold, helium nuclei can fuse with each other, producing carbon and oxygen. Helium fusion ignites in a sudden, dramatic burst called the helium flash. The sun enters a new phase of stability, burning helium in its core and hydrogen in a surrounding shell. This phase lasts only about 100 million years, far shorter than the 10 billion year hydrogen-burning era, before the helium is exhausted as well. What follows is a period of increasing complexity and instability. The sun, now burning in two shells simultaneously, will undergo thermal pulses, periodic brightening events, where the helium shell ignites suddenly, swelling the star dramatically before it contracts again. During this phase, the sun's stellar winds grow enormously powerful, blowing its outer layers into surrounding space. Layer by layer, over millions of years, the sun's atmosphere is expelled outward, forming an expanding cloud of luminous gas. What remains at the center is a hot, dense, collapsed core, roughly the size of Earth, but containing the mass of our entire sun. As this exposed core radiates its intense ultraviolet energy outward into the surrounding gas, that gas lights up in spectacular fashion. It glows in blues, greens, reds, and golds, an expanding iridescent shell of ionized gas called a planetary nebula. Despite the name, this has nothing to do with planets. Early astronomers, peering through primitive telescopes, thought these glowing shells resembled the disk of a planet, and the misleading name stuck. Our sun, in about 5 to 7 billion years, will produce its own planetary nebula, one of the most beautiful objects the universe is capable of creating, and it will expand and glow for tens of thousands of years before the gas disperses into the interstellar medium, seeding future star systems with carbon, oxygen, and nitrogen. At the center of that fading nebula will sit the sun's final form, a white dwarf. It has no nuclear fusion occurring inside. It produces no new energy whatsoever. It shines only from the residual heat stored in its body, cooling slowly like an ember pulled from a dying fire. It is so dense that a teaspoon of its material would weigh about 15 tons. It is held up not by pressure from fusion, but by the quantum mechanical resistance of electrons packed to their absolute physical limit, a phenomenon called electron degeneracy pressure. The white dwarf will cool over billions upon billions of years, fading from brilliant blue-white to yellow to orange to dim red. Eventually, far longer into the future than the current age of the universe, it will cool completely into darkness. A black dwarf, invisible and silent, drifting through a cold and ancient galaxy. And yet, even in that final silence, there is something worth holding on to. The atoms that made up the sun, the hydrogen, the helium, the carbon and oxygen forged in its dying core, will not be gone. They will drift through space, join clouds of interstellar gas, and eventually be drawn into new stars, new solar systems, new planets, perhaps new life. The universe is an extraordinary recycler. Everything that exists was once inside a star. The iron in your blood, the calcium in your bones, the oxygen filling your lungs right now, all of it passed through the interior of stars that lived and died before our sun was ever born. And when our sun finally goes dark, its atoms will go on to build something new. We are not separate from the cosmos. We are made of it. And the story of the sun is, in the deepest sense, the story of us.